Evet Gülsüm'ün şimdi yayındayız.
Okay. Hello, everyone. One of the speakers of today is Melin Okandan. She is an undergraduate student at Bilkent University. And she's going to talk about minimal presentation sizes of numerical semigroups. If you have any questions, you may ask from chat box. If you like, you may start, Melin.
Hi, everyone. Let me share my screen. Okay, so you can see it, right?
Yes, we can see.
Okay. Hello, everyone, and thanks for having me here. Today, I'm going to talk about the cardinality of minimal presentations when a multiplicity and embedding dimension is given. So there are very big words in the title, but we do not know the definitions yet. So in order to understand what this means, what we are looking at, let us first start with defining some basic things. Well, let's set up a certain background. Well, the minimal presentations which are concerned are related to numerical semigroups. So at first we need to know what a numerical semigroup is. So let's start with defining it, what it is. A numerical semigroup is a cofinite subset of natural numbers such that it is closed under addition and it contains zero. So what does a cofinite subset mean? Well, if I take any element in the natural numbers, which is not in this numerical semigroup, and if I collect those elements, I will get a finite set. So I want this set to be finite in order to define a numerical semigroup. Well, okay, so this is a cofinite set, which is closed under addition, contains zero. Well, we can also describe numerical semigroup using a set of generators. Well, this is a great ease because we can write down each element of S considering only these generators. You can hand me any element and I can always find you a combination of those generators. Well, we say that S is generated by N0, N1, all the way up to Nk, if, and this is the collection of the elements A1 times N1 plus A2 times N2, and plus all the way up to AK times Nk, where each AI runs into the natural numbers here, but you may have noticed that this is not any linear combination. This must be positive or either the coefficients are zero. Well, there is no allowance for negative coefficients here. So we are only taking positive linear combinations of those generators and we are getting a numerical semigroup. So let's see it more clearly in a concrete example. Assume that you walk into the McDonald's and you want to buy chicken McNuggets. Well, you know that they are only sold in packages of 6, 9, and 20. For example, there is not a package that contains 13 chicken McNuggets. You need to always buy 6, 9, or 20. Well, how many chicken McNuggets can be bought without breaking apart the package? You are not allowed to leave some McNuggets and for example, take 5 of them, but leave aside 1 of them. So how many chicken McNuggets can be bought in this way? Well, you can just take combinations of 6, 9, or 20, and you can notice that there is no way of buying negative chicken McNuggets, so there is no subtraction here. We are just adding 6, 9, 20 to each other, and the all possible positive combinations will actually give us a numerical semigroup in which the generators are 6, 9, and 20, because we are only allowed to buy packages of 6, 9, and 20 again. So here, what is interesting is that after some number, I believe it is 34 for chicken McNuggets semigroup. After 34, you can ask any size of chicken McNuggets, and I can find you a positive combination of 6, 9, and 20 to let you buy those number of McNuggets. For example, if you want 502 McNuggets, I can guarantee you that you can always buy that many. Well, let us define what multiplicity is. Well, multiplicity is important because we will be looking at minimal presentations of numerical semigroups when the multiplicity is fixed. So what is this? What is a multiplicity? Well, we have said that a numerical semigroup can be written down in terms of its generators. Let S be generated by N0, N1, and all the way up to Nk. Well, here we have an order, N is the smallest element, and generators are written down as a certain order, and Nk is the largest element. And we refer to the smallest generator here, N0, to be the multiplicity of the numerical semigroup. So a multiplicity of a numerical semigroup S is actually the smallest generator, N0 here. Well, if we were to look at, again, the chicken McNuggets semigroup, we know that it is generated by packs of 6, 9, and 20. And you can observe that 6 is the smallest pack you can buy. And here the multiplicity is 6, therefore. Well, if you were to take another numerical semigroup, which is generated by 5, 6, 7, and 8, you can see that there is the smallest generator, which is 5. And here multiplicity is 5. Well, okay, so now we are to define factorization and traits. This will be the main tools to define minimal presentations. So let us see what are these mathematically. Well, again, let's fix a numerical semigroup, which is generated by n0 and 1 all the way up to nk. A factorization z0, z1, zk up to zk is a k plus 1 tuple actually, which gives an element in the numerical semigroup. Well, how can we understand this? For example, you want to buy 18 chicken McNuggets. Well, you can buy three of the 6 packages, right? And you do not have to buy any of the 9 packages or 20 packages. So the factorization of 18, a factorization of 18 will be, in this case, 3, 0, 0, because I am buying 3 of the 6 packs, 0 of the 9 pack, and 0 of the 20 pack. So this is how can we see a factorization. So what is a trait? Trait is a pair when 2 factorizations will give the same element in the numerical semigroup. Here you may have observed that each coordinate of the factorization is multiplied with the corresponding generator. For example, z0 is multiplied with n0, zi is multiplied with ni, zk is multiplied with nk, and we are summing all this up to get this element in the numerical semigroup. Well, when this is a trait, this is a trait when these factorizations actually correspond to the same element. Well, as I said before, 18 chicken nuggets can be obtained by buying 3 of the 6 packs. But there is another way to do that. I can also buy 2 of the 9 packs. I can again, in this way, get 18 chicken McNuggets. This is possible. Well, what will be the factorization of buying two 9 packages? This will be 0 to 0 because I'm buying 0, 6 packages, 2, 9 packages, and again, 0, 20 packages. Well, now here we can see 3, 0, 0 is a factorization, and 0 to 0 is also a factorization of 18 in the chicken McNuggets semigroup. But then this is a trait because I can trade my 3 6 packs with 2 9 packs, and this will actually correspond to the same number of chicken McNuggets. So this is how we construct what is a trait. Well, now we are ready to define what the factorization homomorphism is. Well, the above described procedure is actually giving us a factorization homomorphism. This factorization gamma s is taking k plus 1 tuples, and it is sending it to elements of numerical semigroups. So, as I said before, each coordinate of this set, this k plus 1 tuples will be a coefficient of the generator. Well, what is the kernel congruence? The kernel congruence or kernel of gamma s will be the pairs in this k plus 1 tuples such that gamma sz equals gamma sz prime. Well, what does this mean? This actually means that these 2 factorizations give the same element. Well, we referred to them as before traits. So actually the kernel is a collection of the traits. We are collecting the traits in a set called kernel. So okay, how this is a congruence? Well, first of all, we can define an equivalence relation considering these factorizations. We will say z is related to z prime whenever z and z prime, z comma z prime is a trait, so it is in the kernel. So this is why this is a congruence, because if we take a pair in the kernel, a trait in the kernel, if we add each coordinate another k plus 1 tuple, we will again remain in the kernel. So what does this mean? We before, as you remember, bought 18 chicken McNuggets. There were 2 ways to do it. Either I can buy 3, 0, 0, or I can buy 0, 2, 0. Well, now assume that I want to buy 27. So I am adding 9 more. So in the first case, I will have 3, 1, 0 because I will be needing 1 more 9. And in the second case, I will be 0, 3, 0 because I will have 3 nines. 3 nines. 3 times 9 is 27. And again, 18 plus 9 is also 27. So this gave me two different factorizations, adding the same element to the different sides of the equation, but I again remain in the kernel. So this is in fact a kernel congruence. So it is possible for us to talk about the generators of this kernel congruence. So now we finally arrived to what we meant to describe. Well, what is a presentation? A presentation is a set of traits in terms of which all traits of S can be written. Well, we can describe each of the traits in S using this presentation. But you may have observed that there's no restriction on these presentations. So I can have any presentation. For example, I can have an infinite set. In before, I was describing the traits in 18. There are two ways to factorize 18, as I said before. But I can, for example, multiply 5 with 18, and this will give me another trait. For example, if I were to consider each of these multiplications, I will get infinite number of traits. So this is not very useful. So defining a presentation is not enough for us. This is why we are considering a minimal presentation. We will say that a minimal presentation row, a presentation row is a minimal presentation if no subset of row is a presentation for us. So this is the minimal thing we can get. So we want not just all of the traits, we want a minimal set that will have us describe all of them. So this is a useful thing, in fact. But as you may have noticed, I am not saying anything about uniqueness of writing down minimal presentation. So there can be a number of ways to describe this, and there is no clear way to clear methodology to do it. So we do not know how to write them. But if we have found one way to describe this minimal presentation, then we are good to go. Why? Because of this theorem. Because we are considering the sizes of minimal presentations. Well, and this theorem says that all minimal presentations of a numerical semigroup have the same cardinality. So if we have found out one just single way to count the minimal presentation size, then we are good to go. Before moving on to how we do this, let us see how do we describe actually the traits, given any trait, by using the minimal presentation of S. Well, let's again take our favorite numerical semigroup, which is generated by 6, 9, and 20. Well, here a minimal presentation for is given. Believe me, this is true because it is hard to calculate here in your mind, but we know that this is the minimal presentation for us. What is it? Rho equals, rho has two traits. The first one is 160, 003, and the second trait is 300, 020. Well, now here, what does this mean? If this is a minimal presentation, we know that I can write down each trait happening in S in terms of a combination of these traits. Well, for example, let's take a trait delta. This is a random trait I have taken. This consists of the trait 760043. Well, at first, let's see this is a trait. Well, what does 760 mean? It means that multiply 6 with 7, 9 with 6, and 0 with 20. Okay, so this is giving us 42 plus 54, which is actually 96. Okay, let's look at the other factorization, 043. This means that multiply 6 with 0, multiply 9 with 4, multiply 20 with 3, and then sum these all together. Well, this means that 36 plus again 60. Well, this gives again 96. But then by the definition, this is a trait because there are two different factorizations giving the same element. Well, now, we know that rho is a minimal presentation. This means that we can write delta in terms of the elements of rho. Well, how can we do that? Well, I have described the way in the below. Well, I am summing a copy of the first trait, and then I am multiplying the second trait 2 times, and then I'm summing them up. Well, let's see it. Here in the first coordinate of the first factorization, I am having 1, and here in the second one, I am having 2 times 3. So 1 plus 3 will be 7. Here you can see we have 7. And in the second coordinate, we are summing 6 with 2 times 0. Here we have 6. And in the third coordinate, we are summing 0 with again 0. Here we are again 0. If we were to do this for that one, and summing these together will again give me this one. So I have generated this trait using the traits, copies of traits in the minimal presentation set. So this is a powerful tool. I have just 2 traits, but I can describe infinite number of traits using only these 2 traits.
I have a question. Why we didn't define minimal presentation as a presentation?
Well, it is not a presentation because, as I said, a presentation is a more general thing. A presentation can consist of any traits, any infinite number of traits, but a minimal presentation is a smaller thing, a smaller set, which we want to obtain.
Okay.
Okay, so I'm moving on. Now we have described the way of defining the minimal presentations. Now our question is, finally, how do we count the minimal number of traits? So how can we find the sizes of minimal presentations? Now here the geometry comes into play. Well, we will look at the geometry of minimal presentations. At first, we will define what a poset is, and then we will describe an a priori poset, which is concerning numerical semigroups. And then from here, we will transition into posets, which will give us the sizes of minimal presentations. So bear with us and see what it is. Well, at first, let's start with defining what a partial order is, because this is important. A partial order on a set P is a relation over P which is reflexive, antisymmetric, and transitive. Well, we can let's look at an example. Well, we can take division on natural numbers. Well, you may have noticed that each natural number divides itself. So this means reflexivity. Well, in the natural numbers, for example, if 2 divides 10, there's no way for 10 to divide 2. So this is antisymmetric. And also there's transitivity on the division, because if 2 divides 10 and 10 divides 20, this means that 2 also divides 20. So this is transitivity. This is an easy way to see what a partial order is. So why did we define partial orders in the first place? Because we want to work in posets, and these posets will be actually obtained from the a priori sets. So what is an a priori set? Let us define it. The a priori set for M in S is a set that it is the collection of the elements in S where n minus m is not contained in our numerical semigroup. Well, here we are taking m as the multiplicity, and here we are doing this construction by considering m as the multiplicity. Well, we are not looking at other elements in this case. Well, we can equivalently think of this set as minimal elements of S within each equivalence class modulo M. So what does this mean? I mean that if I were to consider the equivalence classes modulo M, I will find exactly one minimal element in the numerical semigroup that will correspond to this equivalence class. For example, assume that my multiplicity is 6. Then I will have exactly one minimal element that will have equivalence class 5. There's no other element. This is just unique thing. Well, these elements are partially ordered, and if we call this poset the a priori poset of S, then M is the multiplicity. Well, now we will, in the further pages, we will see it in a picture, and it will be a lot easier to think of them. But before doing that, let us define what the poset is. Well, as I said before, the a priori poset consists of the elements which are in certain way corresponding to equivalence classes. Well, a poset is just doing the replacement. I am replacing each element in the a priori poset with its equivalence class. Well, this is what I'm doing actually, and this is leading to a more general thing. Well, if you were to define it formally, well, if a numerical semigroup and multiplicity is given, the poset is the partially ordered set with ground set Zm obtained by replacing each element in the a priori poset with its equivalence class. Well, now you may have thought it, well, there are generators of S, and these generators will be in the a priori set because in fact they are minimal elements and they will correspond to a certain equivalence class, so they satisfy the definition. So each generator except the multiplicity will be most certainly be in the a poset. And the equivalence classes corresponding to those generators will be called atoms, whereas the other elements will be called non-atoms in the Kunz poset. Well, okay, so much work. So let's look at an example to understand. Again, consider the Magnetic semigroup. This is generated by 6, 9, and 20 as before. Okay, then we know, let's assume we know the a preset. A preset is given to us. Well, this can be obtained by a number of calculations. It's not that hard. This is the collection of elements 0, 49, 20, 9, 40, and 29. Well, you can observe that here, except 6, here we have 9 in the a preset, 20 in the a preset. So, okay, how do we draw the a preset? How do we construct the a preset? Well, we construct the elements, but by adding the generators to each other. For example, I sum 20 and 9, and I get 29, and this is in the a preset. And then I add another 20 to 29, and I get another a preset element, which is 49. Well, the arrows are drawn. The partial order is given when an element is sum of the other two elements. For example, here 29 is sum of two elements, so we have drawn 2 arrows here because it will be sum of these. And here an arrow is drawn to the top because 40 is a double of 20. Well, okay, so what did I say before? This is equivalent to modulo classes. So let's examine this. Well, 49, if we consider, is in modulo 6, it is 1. It is 49 equals 48 plus 1. And this means that 49 will be of modulo class 1. And 29 will be equivalent to 2. 9 is most simply will be equivalent to 3 modulo 6. 40 is equivalent to 4. 29 is equivalent to 5. Well, as you see, here we have exactly one element in this a poset that is corresponding to a unique equivalence class. And we are covering all the equivalence classes. 0 is in the bottom, and the generators are placed in just above the bottom. This is the way we construct it. Okay, now we can transition to Kunz poset. As you can remember, we are constructing.
Sorry, I have a question. Why did we stop at 49?
Well, I will get into that because no any sum of generators give us an a preset element. We are not guaranteed that we are every time getting an a preset element. Actually, is the things that move outside of the a poset will give us a way to count the minimal presentation sizes. This is the importance of that. So this is a very good question because there's no random summing here. We are checking always the definition, whether or not we are not remaining in the S when, for example, 69 minus the multiplicity 6 in S. If this is an S, we can't write it down in the a poset. So this is not a random summation. So there is a methodology here, but we are always obtaining the elements by summing copies of generators. Okay, I hope this answers it. Now we are obtaining the Kunz poset. How do we do this? We are replacing each element in the a poset by its equivalence class. So for example, here 49 is equivalent to 1. So we will write 1 in the place of 49. So here 40 is equivalent to 4. We are writing 4 in place of 40. And so on. We are doing this. And then we are obtaining this poset and we are calling it the Kunz poset. And you can see that here are, instead of generators, there are 2 and 3. But again, each element in the Kunz poset is a summation of 2 and 3 in some way. For example, here we have 4 and 2 is 2 plus 2. And here we have 5. 5 is 2 plus 3. And we are obtaining 1 by adding 2 into 5 and taking it modulo 6. So this is giving us the Kunz poset, and Kunz poset elements are also the combinations of its atoms. So here we have the atoms of the Kunz poset as 2 and 3. Well, okay, as I mentioned before, while answering the question, sometimes when you use some generators, you move outside of the a poset. Well, for example, here we do not have any element above 29. We are just adding 20 to 29, we are obtaining 49, but there is no 38 in here, for example. Well, some of these elements with some specification give us automatic elements, and the number of automatic elements will be essential in counting the sizes of minimal presentations. Well, for example, at first, let us define what the support of a set is, and then we will move on to the definition of automatic elements. Well, again, we are taking a k+1 tuple, and then the support of that is actually the collection of its non-zero coordinates. Well, we can define the same thing for a set instead of an element. The support of a set will be the collection of supports of its individual elements. It will be the union of them. And for each I in the support of the set, we will define capital Z minus EI to be the collection of elements such that little z minus EI, where Z is in the subset. So we are defining this in order to have the Alter-Betti element, as we will see shortly. Well, subset B in Z infinity is said to be an Alter-Betti element of P. Well, here do not just tackle with the notation here. Well, this is just the way we are writing it down, but I will explain what does this mean. Well, for every I in support of P, the set P minus EI is equal to some poset element in P. Well, okay, so what does this mean? As we said that, well, in some ways, you move outside of A preposet. So when you move outside of the A preposet, you are actually satisfying the condition A here, even though it is a bit involved definition. This is what it is saying. Well, again, we have another restriction here. We do not just want any element that remains outside of the poset, but we want that the graph of the set to be connected. So what do we understand from the graph? This is the factorizations. Well, okay, so we have factorizations of elements, and how do we draw an edge between them? We draw an edge between them whenever they have a shared coordinates. For example, if we again think of the example of 18, we know that 18 can be written down as two factorizations. One is 3, 0, 0, the other is 0, 2, 0. But you can see that there is no shared coordinates between them. If this were 3, 1, 0, 0, 2, 1, for example, they would have a shared coordinate. They will both have the second coordinate as non-zero. So that we will draw an edge between them in this case. But in the case of 18, there is no edge because there is no shared coordinate between two factorizations of it. So for the Alter-Betti elements, we require them to be connected, and we require them to be outside of the A preposet and eventually the cos poset, because cos poset is just a reflection of the A preposet. Well, okay, so here we can see a picture of Alter-Betti elements. For example, in the cos poset, we all have elements as some linear combinations of the atoms, but here we do not have 3 plus 3. This is actually outside of the poset. So this is an Alter-Betti element. If we were to check it, we will see that easily the graph of B2 is connected. The same is true for B1. And here we obtain that Alter-Betti elements of cos posets can be obtained by considering these two conditions, A and B. Okay, so we have said many things. Let's recap what we did. We defined a minimal presentation. A minimal presentation is a minimal set of traits in terms of which we can write all traits of S. So this is the most fundamental thing we did to calculate the sizes. Okay, what is a cos poset? It is a graph of a partially ordered set corresponding to a modulo multiplicity. So we are looking at elements modulo multiplicity. And we are also defining an Alter-Betti element, which gives us a position in the cos posets where a new element may be added there. Okay, so why we are considering the cos poset? It is because it's a much more general thing. As you see, there are equivalence classes only occurring there, but there may be a ton of numerical semigroups that have the same poset structure, but yet this cos poset can be used to describe all of them. So once we calculate some things for this poset, this can be all generalized. So this is why we are using geometry. We are not getting our hands dirty with calculating one by one the minimal presentations of the chicken McNugget semigroup, the other McNugget semigroup. We are not involving with this. We are just looking at equivalence classes and looking at the general results. Well, okay, so this is a picture or result of what we did. Well, now we are to define one more new thing. This is actually analogous to the definition of trait in a numerical semigroup. You can think of it as we are defining the trait in a Kunz poset. What would a trait be? How a trait will be defined in a Kunz poset? Well, we say that this is a relation, and there is a relation on a poset P if there are multiple paths to an element. For example, let's consider the poset element, Kunz poset element 3 in here. Well, there are two paths that I can go to 3. I am starting from 0. I can at first go to 1 and then go to 2 and then go to 3. Well, there is another way. I can directly go to 4 and then here I am jumping up to 3. So as you can see here, I have multiple paths to an element. So this is actually analogous to the definition of trait, which makes sense why I am defining a relation here. Well, then it makes more sense now because there's an important theorem here that says that minimal presentation size of a numerical semigroup is the sum of number of outer Betty elements of its Kunz poset and the number of relations on its Kunz poset. Well, here we do not have time to discuss this theorem, but if you are interested in how does it come from and how is it constructed, I can post an article about this. It is the section 5 of a Kunz poset 3 paper, which is written by Christopher O'Neill, which describes very well how is this constructed. But now, believe me that this is how we found that a minimal presentation size is actually a summation of those two things. So once we know the number of outer Betty elements of the Kunz poset, once we know the number of relations on the Kunz poset, and if we sum them, we will automatically get the minimal presentation size. So this is an important tool because you may have noticed that while calculating the chicken McNugget semigroup, there were no certain methodology there. We were just trying to find it out. But here, we do not have to prove them one by one. We are just proving it for the Kunz poset, and then it is done. Well, let's look at an example of an application of this. For example, I am taking any numerical semigroup with m-1 generators where multiplicity is m. Well, okay, so you can hand me any numerical semigroup with m-1 generators, and they will have the same poset. Well, right now, ignore the right and green arrows and the things at the above of this picture, but just focus on the black part of this picture. So here we have m-1 generators, okay. So we are to count the size of the minimal presentation, okay. Well, here, there are no relations in this Kunz poset because how did we define it in the first place? We said that there are multiple paths to an element, then there's a relation. But here, you can see that there's only one path to 1, so there is no relation in here, one path to 3. So what does this mean? Since this theorem says that this is the minimal presentation size is the sum of the two things, we will always get that the number of outer Betty elements of the Kunz poset will give the minimal presentation size because there's no relations on the Kunz poset. We will only be focusing on the number of outer Betty elements for this example. And this will be generalized to all numerical semigroups with generators m-1. Okay, so how can we obtain outer Betty elements? First of all, we can double an element here. For example, I can have 1 plus 1, but I will move outside of the Kunz poset. This will give me an element v1, an outer Betty element. Well, for 2, I can do the same thing. I can double 2. Well, as you can observe, I can do it for every atom in this poset. Okay, so this will give me outer Betty elements most certainly. But how many ways are there to do this? Well, since there are m-1 atoms, there are m-1 ways to double an element. Okay, so we are done with it. But there is another way to sum these generators. We can just sum any two pairs together. Okay, so I can, for example, sum 1 with 3, 2 with 4, 5 with 7. I can sum any two pairs, and this will give me outer Betti elements. The graph will be connected. Okay, so I am actually choosing two elements from the atoms to sum together and get an outer Betti element. So how many ways are there to do this? There are m-1 atoms here, and I am choosing two elements to sum. So this is m-1 choose 2 actually. Okay, so I had m-1 doubles and m-1 choose 2 pairs to sum. Okay, and if I were to sum them, m-1 choose 2 plus m-1 will be actually m choose 2. So since there are no other relations here, we conclude from the above theorem that the minimal presentation size of a Kunz poset of the given form will be m choose 2. And this is generalized to any numerical semigroup having this poset formation. Oh, okay, so here we have a table. This table shows certain numerical semigroups with certain minimal presentations. Here, the gray column corresponds to the multiplicity of a given numerical semigroup, and the gray row is corresponding to minimal presentation size. So, for example, if I were to look at the possible minimal presentation sizes for multiplicity 5, I would see that a numerical semigroup can have 1, 2, 3, 5, 6, and 10 as its minimal presentation size, but there is no way to find, for example, a numerical semigroup with multiplicity 8. This is what data is showing to us. This is not a result of a theorem, but this is the data. And from this data, you can observe that this table follows some pattern. So there is something going on here. For example, when we hit a number, for example, for multiplicity 7, for all the numbers less than or equal to 10, I will have a certain minimal presentation size happening there. I can find a numerical semigroup with, for example, minimal presentation size 4. This is possible for me. Well, one other important observation is this. Here you can see red boxes. So these red boxes will correspond to m-1 choose 2 for each multiplicity. So what does this mean? For example, if I were to look at multiplicity 6, I am guaranteed in this table that I will have a minimal presentation size of 5 choose 2. But what is 5 choose 2? It is 10. It is actually these red boxes. And these red boxes are always giving m-1 choose 2 to us. So this is saying something. Okay, now we can look at further results. These are actually the results of this summer. These are new things that in a project that I worked with. So let us see what they are. It is actually looking at the table and taking some educated guesses and then proving it. You may have noticed that for r less than or equal to 2, if the number of generators is m-r, the minimal presentation size has some bounds. So what do we have here? Well, I am looking at just the number of generators of m-2, m-1. So I am not, for example, looking at m-7. I am just restricted to those three things. Well, this is bounded by m-r choose 2 minus 2 and bounded above by m-r choose 2. So we have actually discovered a bound which can describe the minimal presentation sizes. Okay, so this is a new thing. There's still so much to be proven, which are not yet done. Well, actually, we were just looking at in this theorem for the values of r that are less than or equal to 2. But this table shows us that there are so much more patterns here. As I said, before some number, we are having all these possible minimal presentation sizes for given multiplicity. So we can conjecture that for all values between m-r choose 2 minus r and m-r choose 2 plus 1, there is a numerical semigroup with multiplicity m and embedding dimension is m-r. So of course, here we are looking at a much more generalized thing because r is less than m over 2 and m can be any arbitrary thing. And this is improving this. If this can be shown, this can improve the above theorem by setting up a more general lower and upper bound. So this is all that I wanted to speak about. Thank you all for listening. If you have any questions, I'm happy to answer them. Thank you.
Thank you very much. It was great, I think. I'm checking if we have a question from YouTube. Right, we don't have.
Okay.
Okay, thank you very much.
Thank you too.
Let's take a photo.
Okay.
Could you open your cameras, guys? Seda.